Good morning. In the previous section, we have discussed regarding the module 4, that is induction motor design. So, in that class, we have discussed regarding the basics and the output equation of the induction motor. So, in today's class, we are going to discuss the remaining part. So, again, in this case, I'm going to share some of the uh, documents, so which mainly use the information of this particular uh, induction motor. So now here, uh, let us have a look on the previous section what we have covered. So there we have seen the first basics of this particular induction motor. So again the part of the particular induction motor. So here uh, this is particularly the uh, induction motor design. So it is having a two part. One is stator and another one is the rotor. So again, stator is having stator slots, rotor is having rotor slots. Again, in between the stator and rotor, there is a gap, that is air gap. So we have seen the rotor construction as well as the stator construction, and then we have seen the particular introduction to design, what all are the particular parameters we have to consider, and then we have derived the output equation of the induction motor. So this is the derivation, so which mainly shows the particular output equation of a induction motor. So here what we did is, so we have considered the M phase machine with usual notations. So the output of the machine is given by input into efficiency. Then input is M V phase I phase cos pi into 10 raised to minus 3. So for a three-phase machine, whatever the input is there, so again uh, this is 3 V phase I phase cos pi into 10 raised to minus 3. So we have assumed that V phase is equal to E phase, V phase is equal to E phase is equal to the value, that is 4.44 f by T phase kW. So now in this case, we have replaced this particular T phase by Z phase divided by 2. So finally we got this as V phase. So now we know this also, F is equal to P n S divided by 120, and then or it is P small n S divided by 2. So this one we are putting instead of F. So then whatever the output equation is there, so that we know that the output is input into efficiency. um, Again, just by putting this particular value here, so we can get the output. So now after that, this is what the overall particular output equation of a induction motor. So in this way we have derived equation of a induction motor, output equation of a induction motor. So now in today's lecture, so we'll discuss the remaining. So before going to that particular uh, 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 part, so let us have this particular. So what are the different nomenclatures we are giving? So one is the C naught. We have got C naught, that is output coefficient. So this L is gross core length, and the D is the diameter of the stator. Diameter of the status. So now here we need to consider the choice of specific loadings. So mainly depending on the two parameters, so specific loadings, the design will be made. So here in this case, here the main dimensions, so the armature diameter and the stator core D are uh, here, let us say, and the armature core length L also as the main dimensions of a rotating machine. So there are mainly D and L. So D is what? It is the armature diameter of the stator core. So whatever the D here we are showing here, this D, and the second is what? The L. That is the length of the armature core. So these are the main dimensions of the induction motor. Induction motor. So here total loadings, if I say, so this already we have seen in the output equation, total loadings. So there are two loadings. One is the total magnetic loading. What is this? Let us define this. The total magnetic loading is nothing but the total flux around the armature or the stator periphery at the air gap. It is called total magnetic loading. So what is it? So it is the total flux around the armature or the stator periphery at the air gap is called the total magnetic loading. It is given by P phi. It is given by P phi. Now, what is total electric loading? It is nothing but the total number of ampere conductors around the armature or the stator periphery. So it is nothing but the total number of ampere conductors around the armature or stator periphery. So it is IZZ, IZZ. So this is total loading. Now we need to consider the specific loadings. Specific loading. So again, this specific loading is nothing but what? Specific magnetic loading. So it is the average flux density over the air gap of a machine. So whatever the total we have seen, it was total. Now we need to consider specific. So here the average flux density over the air gap of a machine is known as specific magnetic load. So it is given by this total flux around the area gap, we know total flux around the area gap divided by area of flux path at the area. So here we need to take the total flux as P phi and the area of flux path at the area gap as pi d pi d. So this is specific magnetic loading. Now specific electric loading. So the number of armature or stator ampere conductors per meter of armature. Specific electric loading is the number of armature or stator ampere conductors per meter of armature or the stator periphery at the air gap. So again, we need to take the specific electric loading as AC. It is the ratio, that is total armature ampere conductors. So this is IZZ divided by armature periphery at air gap. Armature periphery is given by the pi into d. So this is specific magnetic loading and specific electric loading. So here now we need to consider the choice of specific loadings. How the choice would be. So again, this is also one more design parameter. So choice of specific loadings. So here first we will discuss the choice of specific magnetic loading, or it is air gap flux density. Air gap flux density. So this specific magnetic loading, mainly it is, let us say, whatever the iron losses are there in the particular machine, so they largely depend upon this particular specific magnetic load. So whatever the iron losses are there, so they depend upon area flux density or the specific magnetic loading. Specific magnetic loading. So the limitations of this particular specific magnetic loading or the area flux density is, let us say, flux density in teeth. So in teeth, whatever the flux density is there, so it should be less than 1.8 Tesla. It should be less than 1.8 Tesla. Now, if I say flux density in the core, it is between 1.3 to 1.5 Tesla. 1.3 to 1.5 Tesla. So these are the limitations. Now, what are the advantages of higher value of BAV? So the advantage of higher value of BAV are three. One is the size of the machine is reduced. Size of the machine is reduced. Second, cost of the machine decreases. And the third, the overall capacity increases. Overall capacity increases. So let us say for the 50 hertz machine, whatever the BAV is there, it is 0.35 to zero point 0.6 Tesla, and the suitable value of BAV can be selected from design data handbook. So this is somewhat the specific magnetic loading. Now the specific electric loading, total armature ampere conductor over the periphery. See, whatever the armature ampere conductor are there, so over the periphery it is nothing but your specific electric loading. Now the advantage of higher value of Q, whatever the specific electric loading is there, it is given by Q. So higher value of Q is the advantage is, one is reduced size. If Q increases, the size will reduce, and the reduced cost also. Now disadvantage of higher value of Q, one is the higher amount of copper required. Then second, more copper losses will be there. The third, increased temperature rise. Then the fourth is lower overload capacity. So normal range of that particular specific electric loading is 10,000 ampere conductor per meter to 4,50,000 ampere conductor per meter. The suitable value of Q can be selected from design data handbook again. So the suitable value of the Q can be selected from the design data handbook. Now we'll see the choice of power factor and efficiency. So in this case, the choice of power factor and efficiency under full load conditions will increase with the increase in rating of the machine. So the percentage magnetizing current and losses will be lower for a larger machine than that of a smaller machine. So further, the power factor and efficiency will be higher for a high speed machine than the same rated low speed machine, because of better cooling conditions, so talking into considerations all these factors, the above parameter will vary in a range based on the output of the machine. So similar to BAV and Q, efficiency and power factor values can be selected from the design data handbook. So now we need to study the separation of D and L. How we need to separate the D and L from that particular output equation. So now whatever output equation is there, so it is the relation between D square L product and output of the machine. So it is mainly giving the relation between D square L product and the output of the machine. So to separate D and L for this product, a relation has to be assumed or established. So the following are the various design considerations based on which the suitable ratio between gross length and pole pitch can be assumed. So here, to obtain minimum overall cost, so the whatever the ratio is there, it is 1.5 to 2. 1.5 to 2. So to obtain minimum overall cost, it is 1.5 to 2. Now to obtain good efficiency, it is 1.4 to 1.6. To obtain good overall design, it should be 1.0 to 1.1. To obtain good power factor, it should be 1 to 1.3. Now, as let us say the power frequency, whatever the power frequency is there, so sorry, as the power factor plays a very important role, the performance of induction motor, it is advisable to design an induction motor for best power factor unless specified. So hence, to obtain the best power factor, the following relation will be usually assumed for separation of D and L. So in this case, the pole pitch divided by core length ratio, it is nothing but it is given by the 0.18 divided by pole pitch. 0.18 divided by pole pitch. So now, or it is pi d divided by p divided by L, whatever the pole pitch is there. So it is pi d divided by p, and core length it is L. L is equal to 0.18 divided by pi d divided by p. So now from this we can get the d as 0.135 p root L. 135 p root L. So where d and L are in meter. Where d and L are in meter. So here, using above relation, whatever the relation we have got, that is d is equal to 0.135 p root L. So using this relation, d and L can be separated from d square L product. D square L product. So however, the obtained values of d and L have to satisfy the condition imposed on the value of peripheral speed. Peripheral speed. So in this case, again we need to consider the peripheral speed. So whatever the obtained value of d and L are there, so they have to satisfy the condition imposed on the value of peripheral speed. So for the normal design of induction motors, peripheral speed, for the normal design of induction motors, the calculated diameter of the motor should be such that the peripheral speed must be below 30 meter per second. 30 meter per second. So whatever the peripheral speed is there, so it should be 30 meter per second for the calculated diameter of the motor. So in case of specially designed rotor, the peripheral speed can be 60 meter per second. 60 meter per second. So now we'll have the design of the stator. Design of the stator. So this is about the value of D and L. Before that, we have discussed the specific magnetic loading, specific electric loading. Then now coming to the design of stator. The stator of an induction motor mainly consists of the stator core and the stator slots. Please remember, it consists of stator core and the stator slots. Stator slots. So now, if I say the stator slots, so in general, there are two type of stator slots. So they are employed in induction motors. One is the open type and the semi-closed type. Open type slot and the semi-closed type slots. So operating performance of the induction motor mainly depends upon the shape of the slot, and hence it is important to select suitable slot for the stator slot. So whatever the operating performance is there, it is depending on the shape of the slot. So we need to give an importance to the selection uh, for the slot. So now consider the open slot, how it would be. So here we can see the three uh, main figures, so which are showing the design of this particular open type slot. So the diagram you can see here. So it is something wedge shaped slot like this. This is the structure of open type slot. So now it is semi-enclosed type, semi-closed. So whatever the slot area is there, here it is decreases. Now in this case, a tapered type. So now we will discuss one by one. One is open slot. In this type of slot, the slot opening will be equal to that of the width of the slots. Width of the slots. So here whatever, if I say the slot opening, so it is equal to that of the width of the slot. So in such type of slots, assembly and repair of winding are easy. Repair of windings are easy. So because as the slot area increases, so in order to have that particular repairing, or in order to rectify the fault, it is very easy. So however, such slots uh, will lead to higher area contraction factor and hence poor power factor. Hence poor power factor. So hence these type of slots um, are rarely used in three-phase induction motors. Rarely used in three-phase induction motors. So now semi-closed type slots. So in such type of slots, slot opening is much smaller than the width of the slot, as shown in figure this particular. So hence in this type of slots, assembly of winding is more difficult and takes uh, more time compared to open slots, and hence it is costlier. So, however, the air gap characteristics are better compared to open type slots. So, air gap characteristics are better compared to the open type slots. Now, the tapered slot. So, in this type of slot, also opening will be much smaller. So, tapered slot. But um, however, the slot width will be varying from top of the slot to the bottom of the slot. So if I say this particular uh, whatever a slot area is there, so the width will be varying from top of the slot to the bottom of the slot with minimum width at the bottom as shown in figure at this particular minimum width. So this is regarding the stator slots. Now selection of number of stator slots. So number of stator slots must be properly selected at the design stage. As such, this number affects the weight, cost and operating characteristics of the motor. So, though there are no rules for selecting the number of stator slots, considering the advantages and disadvantages of selecting higher number of slots, comprise has to be set for selecting the number of slots. So, following are the advantages and disadvantages of selecting higher number of slots. So if I select higher number of slots, what will happen? So if I say advantage, so there will be reduced leakage reactance. Second, a reduced tooth pulsation loss, and third is higher overload capacity. So what will be the disadvantage? So if I select um, the more number of higher number of slots, then there will be increased cost, obviously. Then there will be increased weight. The weight of the machine will increase. Then increased magnetizing current, whatever the current which is flowing in the particular motor is there. So it is again the more and increased iron loss. Iron loss will be more as we are using the whatever the slots more, and the material required to have the slot it is also more, hence the losses in the material will be more. So poor cooling, so cooling will be again poor. Then increased temperature rise, then it is reduction in the efficiency. So based on the above comprise is made, and the number of slots per pole per phase may be selected as 3 or more for integral slot winding. However, for fractional slot winding, the number of slots per pole per phase may be selected as um, 3 to 5. So now here, uh, based on the above comprise, based on these particular parameters, so please consider the number of slots per pole per phase may be selected as 3 or more for integral slot winding. So however, for fractional slot winding, number of slots per pole per phase may be selected as 3.5. For the fractional it is 3.5, and for the again integral slotting, it is 3 or more. 3 or more. So selected number of slots should satisfy the consideration of stator slot pitch at the air gap surface. So which should be between 1.5 to 2.5 centimeter. So whatever the selection of the slots is there, it should satisfy the consideration of stator slot pitch. So at the air gap surface, so the it should be that is 1.2 to 2.5 centimeter. Stator slot pitch will be 1.5 to 2.5 centimeter. Now, what is this stator slot pitch at the air gap surface? So this stator slot pitch at the air gap surface will be given by tau SS is equal to pi d divided by SS. SS. So this already we know, pi d. Whatever the SS is there, it is nothing but the number of stator slots. Number of stator slots. So this stator slot pitch will be between 1.5 to 2.5. Please remember. So this is about the particular stator and the design of stator slots. So in the next class, we'll discuss the next topic, that is turns per phase, and again the remaining, that is conductor cross-sectional area, and again we'll solve some examples, and we'll discuss some more design parameters. So thank you.